Given two column vectors A and B of the same dimension, their inner product is obtained by multiplying corresponding components and summing the results. The outcome is a scalar. The definition for inner product of vectors appears quite simple, yet it contains profound geometric insights. From a geometric perspective, the inner product of vectors A and B is equal to the product of their magnitudes, multiplied by the cosine of the angle theta between them. The magnitude of vector A multiplied by the cosine theta represents the projection of A in the direction of B. We refer to this projection length as the scalar projection. Similarly, the magnitude of vector B multiplied by the cosine of theta is the scalar projection of B in the direction of A. For two non-zero vectors A and B, their inner product varies as the angle theta changes. Let's assume that the magnitudes of A and B are fixed. When the angle between A and B is 0 degree, the two vectors point in the same direction, also known as being parallel. In this case, the inner product is maximized. When the angle theta is an acute angle, meaning theta is greater than 0 degree but less than 90 degrees, their inner product is positive. When the angle is a right angle, meaning theta equals 90 degrees, their inner product is 0. At this point, we say that vectors A and B are orthogonal vectors. When the angle is obtuse, meaning theta is greater than 90 degrees but less than 180 degrees, the inner product of A and B is negative. When the angle theta is exactly 180 degrees, the two vectors point in opposite directions, and their inner product is minimized. Now, let's explore relationships between different color vectors in the RGB color space. For red vector E1, green vector E2, and the blue vector E3, it is very easy to calculate that the inner product is 0 for any pair of them. This means that red vector E1, green vector E2, and blue vector E3 are mutually orthogonal, meaning their pairwise angles are all 90 degrees. In other words, E1, E2, E3 form an orthogonal set of vectors. Every vector in the blue-green plane can be written as the linear combination of blue vector and the green vector. This tells us that the red vector is perpendicular or orthogonal to the entire blue-green plane. Similarly, the blue vector is perpendicular to the entire red-green plane, and the green vector is perpendicular to the entire red-blue plane. Through very simple calculations, we can see that the angle between the red vector and the yellow vector is 45 degrees. This means that although the two colors are different, the yellow vector contains some amount of the red vector, indicating that the two colors overlap to some extent. In RGB color space, there are many other pairs of vectors with 45-degree angle. Try to find them yourself. Additionally, the angle between the yellow vector and the cyan vector is 60 degrees. I encourage you to compute this result by yourself. The closer the angle is to 0 degree, the more similar the two color vectors are, meaning the color vectors are more alike and their overlap is higher. The closer the angle is to 90 degrees, the more different the two color vectors are, meaning the colors are more distinct and their overlap is lower. In the next video, we'll explore how the inner product is applied to scalar projection and vector projection.